both of them.
Think hardware. Yeah, we are building a processor. So now the correct question would be, in the processor, what do these bits perform? So what kind of special unit inside of your processor should be, and what should that unit do with Sure, fine. It's okay. So you have different right? And you have some branch of equal. Now the question is, do they have the same comments? Right? They have the different. So yeah, so now, well, not different parts of the processor. Now just imagine some sort of a in your own head, when you look into, let's say that I give you a pattern. And I ask you what instruction. I give you like 10000100010 something. And I ask you what instruction that is. So how would you decide what kind of instruction that was? Just when you go breaking their custom. So first 6 is the output, right? So you take the output bits and what do you do with those output bits? Will translate. Exactly. So shouldn't your processor also do something like that? It should just look up and find out what instruction that is. Because add is different than subtract. Add is E plus C, whereas subtract is E minus C. Right? And similarly, there are some other instructions, for example, shift logic left, shift logic right, and correct. So output is going to a control function, control unit that decodes what instruction is. Right? Exactly. And similarly, these bits RS, RT, RD, you're using them to find out what registers these. So think about hardware. Where should these bits go? Right?
That's the around. So,
all right.
Opening goes in the way next to
operating system is still too high level. Right now, we are dealing with processing. You're doing
Oh.
So think about hardware.
Oh, all right.
The thing is also hardware and I understand that if you 32-bit 0. Can I ask you what instruction that is?
Oh, they go to AALU.
Which one of these fields determines
ALU, arithmetic logic unit. I don't know.
Well, not technically all of it. For example, if you consider the I format instructions, you can have LW in your branch is equal, and both of them have RS, RT, and a constant address immediate value. So what will differentiate a BEQ instruction from a load word instruction? They are exact, right? So when you build the hardware, you need to have a special decoder that determines what kind of instruction, right? Because these different instructions should be different things. Add performs A plus B, subtract performs A minus B. You're comparing two values for, let's say, branching it equal. Technically, you're performing a subtraction and seeing whether the result is 0 or not. If the result is 0, then that means it's true.
Here.
Yeah. Yeah. So off would require a decoding unit. And what about RS, RT, RD? Where do you think these should go? Yes.
Arithmetic logic unit.
Huh?
ALU.
Arithmetic directly to arithmetic and logic unit?
No.
Well, RS, RT, RD, technically, they are addresses of registers. They are giving you register numbers. You look up at those registers to get your actual value, which then go to the arithmetic and logic unit. So now, tell me, where should RS, RT, RD go?
Register file.
Very good. Register file. How did you know that? Did you? Okay.
I studied before on YouTube.
Oh, very good. Excellent. That's the spirit. Very nice. So RSRTRD should go into the register file. So here's what we are going to do next. Using these encoding types and one format at a time, we are going to build our hardware. Now, building the hardware process requires a little bit of pencil and paper because now you'll be in the shoes of computer architects. Now, architects, they initially make their blueprint using pencil and paper. They do a lot of drafting and stuff. And therefore, what I would like for you to do is turn the lids of your laptops halfway down, please. Okay, excellent. Now, this is our plan. This is our plan. In your project number 3, you have been encoding 3 instruction types, the R type, there has been I type instructions, and branching and jump instruction. Well, branching technically falls under I type, but these 3 can be also grouped in this manner. For building our hardware, this is going to be our assumption. We are only going to consider 2 R type instructions, just an add instruction and a subtract instruction. Each of these instructions takes 3 operands, S1, S2, S3, like 3 registers. We are also going to consider memory reference instructions like load word and store word, and branching instruction, branch if equal and J. Starting with R type, we are going to build our CPU. We are going to identify what components are required to perform these different formatting instructions. And then we'll merge them together in hardware, all right? Because your processor is actually a single hardware. There is no separate dedicated unit only for R type instruction, no separate unit just for the I type instruction. They are actually all the same, and they are unified using digital logic components like multiplexers, right? Using those, they are merged together so that your processor can run really very fast. So this is how we are going to build our CPU. We are going to first determine the instruction fetch hardware, because let's be honest, processors, they have to execute the instructions. Then we'll build our R type instruction. Then we'll build our memory reference type instruction and merge them together. And then finally, we will develop our branching and jump instructions and merge the entire hardware together. By the end of this whole agenda, you will have your CPU that is able to execute the R type instructions, memory instructions, and branching instruction. Now, for today's class, we're only going to focus on R type and the memory type instructions. We are going to build our hardware just for that. Now, let me ask you this question. How many of us have played with Legos before? Okay. How many of us have built like crazy structures like Battlestar stuff? There you go. Excellent, excellent. Wow, I have never done that actually, right? So what is the key to building those components? Let's say that I have 2 pieces, right? How should I find out whether they go together or not? The instruction manual, okay. And if I don't have the instruction manual, I can just see the components and see whether they fit together or not, right? Yeah. Right? Okay. So yeah, so we have 2 pieces. We'll see what are the output like thingies for this particular block, and what are the input kind of thingies, and let's see if they go together or not, right? And that's how you decide. In the similar manner, when we design our processor, we will determine what components we require, and we will determine what are the inputs and what are the outputs. Once we have decided those, we are going to just use them as Lego pieces and build our hardware. So here's what I would like for you to do next. I would like for you to think, what pieces do you need to build a data path? Now, please remember, we are starting off with the R type instruction. We are starting off with the R type instruction, and a typical R type instruction is an add instruction. We are just considering add and sub. So let's say S1, S2, S3. In hardware, it should perform S1 is equal to S2 plus S3. Your hardware should look up at the value of S2. It should look up at the value of S3 by using their register numbers, add them together using a special unit, and then store it back into S1. Please discuss with each other and determine what are the pieces needed to build the data path. Also remember that this add instruction has to be stored somewhere. It has to be stored somewhere and it has to be fetched first before this can happen. Your MIPS instructions, they should be stored in some special memory from where they can be fetched, and then they can be executed, and then the processor proceeds to the next instruction. So please have a chat with each other. What pieces do you need to build your data path now to fetch this instruction and execute it? Now, you think one of the assets where you have layers that you have worked before?
Like yeah. Data from register S2 and S3 combined goes to S1.
One answer you already gave. The component required. It's a register file.
You need memory, you need program counter, you need instruction register, you need ALU.
All right. Now please have a chat with each other. I want you to make some noise, and I will ask individual groups what piece do they think is required now. So please have an active discussion.
You remember you were saying every instruction is 4 bytes. So here, hello, 0 and 4 and 8. I found this image online. This is the register file. This is our file, ASM, not ASM. Row 1, row 0, row 0, row 1. This is ALU. Arithmetic logic. So like. In memory, 0, 4, 8, 12, this is like a line. So first number 4 bytes. Remember in the counter, like every time it plus 4 plus 4. Of course, you want to take some instruction from the instruction register. Yes, the thing. Yes, yes. Instruction. Control. Controlling.
Please keep having a discussion. You have 2 more minutes to make your list of pieces, your Lego pieces, to build our data path.
We are ready. Hello.
Thank you. All right, 1 more minute to make your list of your Lego pieces to build the data path. Okay, so I sense a lull here, so it means that your list is ready. Hey, all right. All right, so Ben and team. So what do you think? Give me a Lego piece required to build the data path. And our Datapath should be able to do this. It should be able to fetch the instruction from the instruction memory, identify the instruction, look up the register values, in this case, add them up together, store the result back, and then move on to the next instruction. So give me a piece in this architecture.
I suppose the first piece we would need like opcode.
Well, opcodes technically is just a bit, right? But we are looking into units. We are looking into units. For example, Ramesh told us that you would require a register file. That's a unit. Definitely a piece of this data path, because the register file is the place where all the registers are grouped together. And using the register numbers, the RS, RT, RD, you can look up at their values. So register file will definitely be a piece. Think about some other piece. Have a chat with your peers for the next 30 seconds. And in the meantime, I'll move on to the next and I'll come back to you. Okay, all right. So how about Manohar and T? Any data path piece that you think would be required to perform this operation?
Yeah.
Definitely you'll require an instruction file, because which we'll call as instruction memory. There you go, because CPU has to fetch from the instruction memory. Now, since they are stored in memory, those have addresses. Now, have you ever come across an entity that stores those addresses so that the processor can move on to the next? Some sort of a counter, maybe, right? Which keeps counting, which keeps incrementing by 4. PC, there you go. Program counter will be another piece. So far we have register file from Rames's team. We have instruction memory from your team and the program counter. What else? So Ben, were you able to talk with your peers, Marcos? So this is done by lookup in the register values is done by the register file. What about this? Adding them together. What do you need to add them up together? What digital logic component you have seen in ECPE170 that adds 2 values together? An adder, very good. So you require an adder, meaning you require some sort of an arithmetic and logic unit, which not only performs addition, but something more like subtraction as well, maybe shifting the bits. But for now, we'll call it the arithmetic and logic unit. Very good. What other components do you think will require? When you look up at the processor specification, what really impresses you about it? Number of cores, okay, that's a very high level stuff. What other things? Think about days of the year. Memory, okay, well, the cache, exactly. Speed, determined by? Megahertz, the clock speed, right? Very good, the clock speed. So you would need a clock train to perform execution of these instructions. So at every clock tick, a new instruction should be executed, right? So you would require a clock tick. Okay, all right. So these are the components you will require. You will definitely require the arithmetic and logic unit to perform the addition. This arithmetic and logic unit can do a lot of things. Now carefully observe what are the different components, what are the different outputs. Inputs are 2 data values of 32-bit, because we are dealing with MIPS 32 bits. Then you'll get an ALU result, and then there's one other result called 0. It's a flag essentially. 0 flag is often used to determine whether the 2 values are same or not. Essentially what happens is your ALU performs a subtraction, A minus B, and if the result is 0, then this flag is raised. And using this flag, you determine whether the instructions are equal or not, right? And it is quite useful for instructions like branch if equal, even in the case of branch if not equal. So you definitely require an ALU. You will require an instruction memory. You will require your register file. You will require your program counter. And you will also require your data memory. Well, not so much for the R-type instruction, but definitely for the memory type instructions. You will require a data memory. Now, please remember that instruction memory and data memory they are separate from each other. They are separate in this architecture. You may require a unit that performs just the addition, because sometimes you do not need a clunky unit like ALU. Now, ALU happens to be a clunky unit. Why? Because it is doing a lot of things. It can do add, it can do subtract, it can do shift logic left, it can do shift logic right. So it's a clunky unit. If I have to have in my processor multiple adder units, I do not need to use ALU one more time. Instead, what I can do is I can use an adder unit which just performs addition. It's a much simpler hardware and easy to replicate versus ALU. So let's say that we need add as well. We would require multiplexers. Now, when do you require multiplexers? Think about it. In ECPE170, did you come across multiplexers? Yeah? Okay. Now, when did you use those multiplexers? Or rather, what is the job of a multiplexer? Think about it. Think from your knowledge of ECPE170 and touch base with your peers and tell me, what does a multiplexer perform? Don't know.
That's bad.
That's bad part. No. It's going to be much fun. Because you are going to see all of these things in action. Now you're going to build a processor.
Show it to us.
Huh?
Everything in your hands.
Everything is in my hands.
I will not be Marxist man. But I don't really like, you know, I think like it's like one input allows decision. You were good in the ECPE170. So was the one.
Oh, I remember he's like inputs and you just like.
Okay. A multiplexer has two inputs and two outputs. Two inputs and one output. Two cross one multiplexer, for example. So let me show you a case. Ramesh and Gapur, can you come please? Yeah. Now you're going to see something else, something fun. So these two are two different individuals stand side by side. Okay. Now both of you sit on the chair. Sit on the chair.
You go first.
See, now there's a confusion, right?
Yeah.
There was a confusion.
Yeah,
If
yeah.
they attempted to sit both on the chair, it would be like,
Yeah.
right?
Good.
But instead, what I'm going to see, okay, I'm going to select, if it is 0, then Ramesh will sit. If it is 1, then Gafur will sit. 1.
Okay.
Ramesh was able to sit, right? Go back, Ramesh. Gafur was able to sit. If I say 0, essentially what I've done is using 0 and 1, I selected which data I would like to pass on.
Okay.
And this system is actually a multiplexer.
So like you can give like two different instructions, but one will be on.
One will come out. One can come out
okay.
exactly based on which one you are selecting. If it is a 0, then 0 will come out. If it is a 1, then 1 will come out. And this resolves a lot of data clashes within the processor, right? So multiplexers, they are the data selectors. They are used to resolve ambiguities between what data needs to pass on into a data bus or a data path, right? Now, did you fall in love with multiplexer? A little bit, yeah. At least infatuated with it a little bit. No, okay, all right, okay. Some other components that you require will be the clock tree, because everything will happen at the positive edge of the clock, and the entire instruction will be completed between two positive edges of the clock, right? So these are some of the components you would require. So please make a note of these Lego components. Now, Lego lovers, I would have you build this data path together using these components. So please note these different data paths using pencil and paper. Please note, I will make these slides available to you on Canvas. So you don't have to draw it using your computer. Just pencil and paper will be good. Okay. So these are the components, right? You have ALU, you have adder, you have standalone adder, you have instruction, you have data memory, you have register, you have program counter, and a clock tree. Now, clock will be implicit, so we will not be drawing a clocking unit, right? Because that's more job of computer engineers who are dealing with, clocking circuits. So we are not going to worry about that. We are actively going to be using the ALU, adder, data memory, instruction memory, registers, and counter. We are not merging our hardware yet. Therefore, muxes will take a backseat for now. When the time comes for merging the hardware, think multiplexers, okay? So when we are going to merge two streams or multiple streams together, think about multiplexers. Okay, now one of the keys in Lego design is the pieces should fit, right? So every piece should have some sort of a bumps and holes in them so that things can fit in together. And similarly, here we need to determine what are the input and output ports for instruction memory and data memory and even register file. So think about instruction memory and registers. Think about them. What should be the input ports and what should be the output ports for register memory and instruction memory? Think about this instruction: add $S1, $S2, $S3. Now these should go in register file. These give you the addresses of the registers in the register file from where the data is fetched. So what should go in and what should come out of these files? Think about it. Please make some noise and discuss. Yes. Goal of instruction memory is to spit out instructions. Yeah, and because we are dealing with
no, it's not good.
memory. So that's like the look at memory address. So this instruction look at memory address and how instructions. What you do in instruction memory. If you see the memory address, and the instruction is now, you think about the add instructions. From where and outcomes those values executed. Right? At the same time, a different unit adds them up together and puts the result back in the next one. So now, what should go in the register file and what should come out? How's it going, that? Right. Yeah. Okay. So did you guys think about the register file? Yeah. What are they? Very good. Now, offset is a different ballgame. So register file is just to read register values. That's all it is. Okay. So only the register related things will go. Okay. Very good. Very good. Okay. All right. Awesome. So the goal of the instruction memory is to spit out the instructions. And how it does it? Well, you supply it the instruction address, and out comes the instruction. The description is as simple as that. You supply the instruction, and out comes the instruction. You supply the instruction address, and out comes the instruction, right? So what is the input to the instruction memory?
Instruction address.
Instruction address. What is the output?
Instruction itself.
Instruction itself. Very good. So here's the deal. Oops. Okay. Now, with instruction memory, in goes the instruction address and out comes the instruction. Now, when you consider this add instruction, right? This is RS register, this is RT, and this is RD. Now, this is what has to happen. Using the RS register, you look up its value. Using the address of the RT register, you look up its value. A separate unit adds them up together, produces a result, and send it back to the register file. Where do you want to put that value in the register file? Well, it is specified by the RD instruction. Now determine what should go in as the input to your register file. Is RS an input? Yes, move. RS is your source. RT is usually the second operand, which can be either the source or a destination both. But RD is always a destination. Nonetheless, they are the register addresses. They give you the register number where you can specify, which you can specify to look up the value which is present there. For example, if I'm like, hey, what is the value at register location 15? Then there will be a 32-bit value present there. Now, is RS an input to register file? Yes. What about RT? Is it an input? RT is also an input. What about RD?
No.
Are you sure? Well, whatever value we have produced, we need to put it back into the register file. And the question is, where do you want to put it? I have to tell the register file in exactly which location I want to put it. And I use RD to specify that. Now tell me, is RD an input or output?
Yeah.
It's an input. Very good. What are the other inputs to your register file? Here, I want to write the value back. So the sum itself, is it an input or an output? It's an input, right? I want to store it back in the register RD. So since I want to store a value back, I need to use the sum as an input. So there's going to be some sort of a data that is going into your register file. And by specifying RD, you're telling where to put that data. Okay. All right. So without further ado, let me give you those. So these are the different items. You would need the register address, 5 bits, which is actually the RS, the very first one that you see. That is the RS register. You need to specify those 5 bits to tell your register file which register you want to read. When you specify that, out comes its data. So for example, when I specify S2, I will specify the register number of S2 there, and out will come the value which is stored in S2. Similarly, I need to specify the register number of RT. For example, in this case, it's S3. When I specify the 5 bits code for S3, out comes the value of S3. Your register file should be able to spit out the data, right? And how it does? You specify the register numbers and it will spit out the data for you. So you specify 2 register addresses, RS and RT, and out come data 1 and data 2. Now, your register file should also be able to store the value back into one of the registers. Now the question is, what value do you want to store? And the next important question is, where do you want to store? So write register. In this port, in comes the register address where you would like to place your data, right? This specifies exactly where I want to place the data, and then the data itself. So these are the different ports of a register file. So please make a note of these different ports and have a chat with your peers for the next 2 minutes and let me know if you have any questions. Yes. So data is when you perform this addition, you get an output.
So they will get a like add module under that, which goes
Somewhere.
the result of the data, right?
Yeah.
So like instead of data, what we could use like operation.
Well, no.
It could be.
So see, regardless of the operation, you're producing a value.
Yeah, it's a result. Result.
And data is a fancy way of saying result.
Yeah.
Okay. So irrespective of what operation is performed, if you want to store it, data, the data bits will come in.
Thank you.
All right. So are we good with register files? The input and output? All in favor, please raise your hands.
Register file output will be data, right?
Well, data, yes. Okay, so let me repeat this one more time. The goal of the register file is to read what values are present in the registers, and at the same time, it should be able to store the values into these registers. Now, in order to do that, in order to read the two registers, you need to specify two register address buses. One is the register address 5 bits, which is the RS, and then the second one is the RT. And when you supply them, out come their respective values, read data 1 and read data 2. Your register file should be able to store the data back at certain register locations. So what do you need for it? You need the data bits itself, the entity that you would like to store in the register file, and the location where you would like to store it. And therefore, these are the ports of a register file. So far, so good? Okay. Now I would like for you to put the shoes of a computer architect and design an instruction fetching hardware for me. All you need to do is use the Lego pieces. Use the Lego pieces and convert this code into a flowchart using those Lego pieces. What it should be able to do is it should be able to look up at the register memory using the program counter. Out comes the instruction. At the same time, PC is incremented by 4. In this case, for space constraints, I have abbreviated program counter as PC. So PC acts like a program counter. So all the Lego designers in the class, you have your Lego pieces, you have the instruction given in front of you. Use that instruction and get the Lego pieces together. Now these are the Lego pieces you have: an adder, an ALU, you have the program counter PC itself, you have instruction memory, in goes the address, and out comes the instruction. And then you have data memory and register file. But using these Lego pieces and the instruction on the slide, please join your Lego blocks together. I will randomly ask a group to show their work. Yeah, those four specifics. Yeah, how much you bring them together to do this, and this, to do this.
Yeah, you're going to
Yes.
Excuse me, sorry. Please work with your peers. I'll randomly ask a group to come on the board and draw it. Please have a chat and actively discuss how would you bring these pieces together to perform this. Into the instruction memory, in goes the program counter, out comes an instruction. At the same time, program counter is incremented by 4. Please don't be shy to ask me any questions. Okay, so let's take a look at the instructions. Action next to that is counter. So whatever program counter has, it is given to the instruction memory, right? And outwards, but then the program counter is also given by 4. So just bring the Lego parts together and see where you go. And if you first bring the Lego pieces to the instruction, and then add on to it, EC is equal to PC plus. Okay, and then so those are the blocks that you'll be using. How's it doing there? Okay. The reason why in order to go to the next instruction, you have to skip 4 bytes. And that's why you have you still do a +4, and that's why you haven't added first applying this instruction. Maybe I guess there's 2 inputs. So okay. PC, okay. What instruction memory is actually
at the same time,
PC.
just like yes, on the right. So the things over the useful.
2 inputs should be gained to
logic.
Okay. Yeah. So whatever PC currently is, it is going into the instruction memory. At the same time, it is added by 4. At the same time, out of that. Right now, you're doing PC plus PC. So out of PC, what you're doing is PC plus PC. So this equals 4.
Do we need ALU or can we do it without ALU?
ALU is a clunky unit. All you need to do is PC plus 4.
Yes. So okay.
Let's see what's happening. Out comes 2 PC and then out comes 2 PC and then add them up. So now it's just your hardware. But you're on the very right track. Awesome. Good job. Good job. Good job. Yeah. Okay. All right. Okay. So Jason and team, could you please come on the here you go. I'll just erase this for you real quick. All right, bringing the Lego pieces together. There you go, perfect. Excellent. Very good job, thank you. If I were to be a little bit more specific, I would also specify these arrows, right? These arrows are going to tell me exactly what is the direction of the data. Like so. In goes the instruction address, right? Because program counter holds the address of the next instruction. So see what's happening. Using the program counter, you're looking up at the instruction. At the same time, program counter is updated and it moves on to the next instruction, right? Okay. All right. Well, I have slides for this for you. So let me show you the slides and I will eventually upload it on Canvas. So you will have everything. All right, so this is what is going to happen, right? You have the instruction memory, you have the program counter. Program counter holds the address from where the next instruction has to be fetched. So in goes the address and out comes the instruction. At the same time, the program counter is incremented by 4 and it is fed back. And there you go. We have brought our Lego pieces together to do instruction is equal to instruction memory PC and PC is equal to PC plus 4. So carefully observe this flowchart for the next 1 minute with your peers. Discuss, make sure that they understand it, and let me know if you have any questions. Yes.
Mine is a little bit different. Would you accept it?
Oh, okay. Well, the direction is a little bit messed up.
I think it is.
Oh, I may have. So program count. Oh, okay. Actually, there's a little bit of mistake here. They should have, because what you're doing is you're doing instruction memory PC plus 4 because you're sending PC plus 4 in. Instead, it should be this. Okay, and this should disappear, and this should be fed back to program. Okay, but sorry, you were on the right track. Yeah, I thought you had it. It's okay. Yeah, like on the slide. You can just take a look into the slide, right? Okay. So are we good with this instruction fetching hardware? Very nice. So that was level 1, Lego player. Now, are you ready for Lego level 2? Level 2 is this. These are your Lego pieces. So please carefully observe on the slides. These are your Lego pieces. Your ALU, your instruction memory, your add unit. You again have to reuse your instruction fetching hardware and use the register files to implement and add instruction. This time you would use the ALU. Now this is what the add instruction is doing. Add instruction is using the address of register RS, which is S2. It looks up at the value. Out comes the data 1. RT should be fed to register 2. Out should come the data 2. And whatever sum has been produced by the ALU, it should be placed back into the registers by looking up at the RD. Where exactly do you want to write? You would like to write it at RD. So please bring these Lego pieces together and create your R-type hardware. Yes. Yeah, ALU result is the acquisition result. Yeah. Yeah, so essentially, you would further extend it. This unit will always be there, right? Now with this instruction, it's a 32-bit instruction, right? And that 32-bit instruction has different fields. Some of them are RS, RT, RD. You need to determine which one of those bits are RS, RT, and RD, and then shove it in the correct input box. Right? Very good. Now here's the deal. This is something important to know. Your instruction bit is 32, right? So Logan and team. Okay. Instruction bit is 32, out of which the first 6 bits is opcode. Right now, we don't need it because we are just focusing on R-type hardware. We know that it's going to do only add or sub. Just that, right? Right now, we are just using the add as an example. So we don't worry about about opcode just yet. Next 5 bits are RS, which tells you what should be the register RS address. Next 5 bits are RT, then followed by RT, RD. So RS, RT, RD. Those are the 5 bits that you have to take out from the instruction. So let me repeat this one more time. Instruction 31, 30, 29, 28, 27, 26. Instruction 31 to 26, it's opcode. Right now you don't have to worry about it. Then instruction 25 to 21, those are the RS bits. Determine where they should go in. Then from 20 to 60 are the RT bits. Determine where they should go in. Then 15 to 11, 15, 14, 13, 12, 11. 15 to 11 are RD. Determine where they should go in. To be honest, right now, this information is not required because we have the consequences. Yeah. Right now, our goal is to build the process, and we need to bring these components together. These people are build the process. Yeah. How would you like the task or how it's happening? That's the add instruction right there. And also RD is the hardware. T doesn't actually stand for so for now, for all practical purposes, what's your second? So do specify RS and RT bits to reach their output. Because we need to read their data, not additional. And then you output from data one and data two, to add using a special unit. No, you choose which unit you want to use, and then using the RD bits. Okay, you will use it to specify which register has the unit. So now bring those components.
Yeah.
Okay. Please take the next 5 minutes to finalize your flow chart, your Lego pieces. Bring them together. Yes. No. Here, it is the instruction address where you have the instruction. When I provide instruction address, out comes this 32-bit instruction. How do you define the address? Using program counter.
So program counter should go there.
Program counter should go there.
And it's going to be 32-bit.
Yeah.
Can I branch it like 5 ways?
Yeah, you can. Yeah. Yep. Very good.
Do I need ALU here?
You require an ALU to perform the addition.
Okay, and why not add?
Why not add? The reason is, that's a very good question. Now, we are building an R-type hardware. Now, right now, you're building the hardware that just does an addition. But in future, you want to make it do subtraction. Then maybe later shifting operation, right? So you want to evolve this hardware.
Okay, so for ALU, one input will be add, and
One input will be read data 1, and the other input will be read data 2.
for ALU,
For
we
ALU,
will add is not going to be used at all, right? It's
in
somewhere.
this case, add is only going to be used to go to the next instruction.
Yeah,
PC
yeah,
plus 4.
Thank you.
Very good. Yes. Okay. Very good. This requires a little bit of more. Okay. Now, jazz hands. Your concentration here is jazz hands, right? Okay. So in digital logic, we have the concept of buses. A bus is defined as multi-bit input. For example, if you have this data which is for 32 bits, it's actually kind of a bus. Instruction, it is also 32 bits. So that's also actually a bus. In digital logic, you can also do bit slicing, meaning you can read only specific bits of these different buses. So for example, when you consider your instruction, which is 32 bits, you can do some bit slicing, meaning instruction 31 to 26 is actually your opcode. Then instruction 25 to 21 is your RS register. Specifically, it is the RS register number. Instruction 20 to 16 is the RT register number. Similarly, instruction 15 to 11 is RD register number. So when your instruction comes out of the instruction memory, you can do bit slicing and get these individual bits. Now what you need to do is determine where would these three entities go on the left side of the register file, and just make that connection. Yes. ALU will be outside. It will be just imagine ALU right here, because ALU has two inputs, right?
And so ALU comes one as a result to the event right down there. What instructions are here or no?
Yeah, well, instruction memory. From instruction memory, you can get the individual bits to access RT, RD, and RS.
And they go
to
the but this instruction is inside. I'm not writing this that right. The logic that you wrote down.
No, that is actually coming off here.
Yeah, but that's something inside, right? So
How do you say that's inside? So from instruction memory, out will come 32 bits bus. And then there will be a little bit of piece of hardware that is going to do that for you. It's going to extract the individual bits.
yes. So for outside, if I just write OP, RS, RT, RG, is enough. So it's not required to like write the parentheses and stuff like 32 to 26.
I would still write it because it clarifies exactly which bits to.
That's what I meant by
All right, so please take 2 minutes to discuss. All right, so let me just check around. Heck yeah. All right. Okay, some more design.
Number.
Very nice. Good job.
So like it comes RS.
Got it.
First,
Okay.
RS, right? S1 get it. S2 get it.
Okay.
Issue that integer file. I will special it or then can correct it.
Okay. All right.
Now, are you ready to see how those Lego pieces can be brought together? All right, okay. Well, this is your instruction fetching hardware, right? Program counter goes into the instruction memory, out comes the instruction. At the same time, it is incremented by 4 and fed back. So program counter is updated. Now, when the instruction memory comes out, there are certain fields to it. The first 6 bits happen to be opcode, OP, which we will not worry about just yet because we are only focusing on the R-type hardware. The next 5 bits are going to be RS, 25 to 21. The next 5 bits, 20 to 26, is R. 20 to 16 is RT. The next 5 bits, 15 to 11, is RD. Now, please note, this is very important to specify. The brackets and the bit numbers, those are very critical to mention in a data sheet because it exactly tells you which bits to read. Because if you read incorrect bits, hell will break loose, right? So RS is 25 to 21, RT is 20 to 16, RD is 15 to 11. Now this is how I'm going to fix it. RS goes into register 1. So I'm specifying which register I want to read. Whatever I specify, out will come the data that is residing at that register. So when I specify register number S2, out will come whatever S2 is storing, some 32-bit value. Similarly, when I specify RT, out will come data 2. Read data 1 and read data 2 will be fed to the ALU to perform RS S2 plus S3, right? That will give me the sum. And then this sum has to be written back into the registers. Where it has to be written? Well, that will be specified by the RD register. So I connect 15 to 11 to this port, right register, which specifies where the data has to be written. And that's how you'll build your R-type hardware. So let me visualize this one more time for you. Instruction hardware, bit slicing, connect to the ports. RS goes to register 1, RT goes to register 2, RD goes to the right register. When RS and RT go to register 1 and register 2, read register 1 and read register 2, out come read data 1 and read data 2, which are added. The result is then written back into the register. And that's how you build your R-type hardware.
I have a question.
Uh-huh.
So like from here to here, like how does the processor know like what's the operation we are doing? I thought we are gonna fetch add to.
That's a very good question. How does the processor know what instruction we are doing? And that is determined by a special unit called the control unit. Now, there is a reason why we discuss control unit towards the end when we have brought everything up together. The reason is control unit is a little bit complicated. So we leave that complicated part to the end. That's a very good question. Once we build right now we have built our R-type hardware. We'll build our memory type hardware. We'll build our branching type hardware, bring them together. Once we have brought them together, the final step will be to make the control unit, which determines what type of operation it is. Very good question. All right, so please have a chat with each other about this R-type hardware. This is what I would like for you to do. I would like for you to pair up. The person sitting on the right should explain the R-type hardware to the person sitting on the left. And then I'll randomly call upon a group and ask the person sitting on the left to explain what the right partner explained. Okay? So here's what you're going to do. The partner sitting on the right is going to explain this R-type hardware. Then person sitting on the left will explain to the entire class if I ask, what was that explanation? So please get explaining.
Not subtraction, ALU. And actually, yes, there is one question. Okay. Who's on the right? You're. Yeah. Divided. First is RP, and then first goes RS, second goes RP, third goes RP. It is not the full class. Add that. Yeah. Right, right, right. It's like right. It says the right. No, because program counter in context 4.
All right.
Next slide.
Okay, jazz hands here. All right. Okay. So let's see. I guess there was a team of 3. Okay. All right. So yeah, but you were left to. Okay. So how about this? Yukio, can you take the lead to explain this? And Logan, you are going to support Yukio. If Yukio is having some confusion or anything, you are going to add up on that. Okay. So you are going to work together, but Yukio, you're going to take the lead and explain this.
Okay, so we start if we split everything up. So the RD, we know where the register is going to be. The RS and RT, read those. And then we go to the, we do something with it. And then after we do something with it, we can follow it back and write it to the register.
Perfect. Very good. That's exactly how the R-type data path works. Cool. Okay. Now let's have a review of what we have discussed so far. What we are trying to do here is we are designing a single cycle data path. Now, I did not introduce what single cycle actually means. It's quite simple. The single cycle data path means that an entire instruction is going to be executed between two successive positive edges of the clock. So starting at first positive edge, an instruction starts getting executed, and until the next positive edge, that instruction would have been executed. So the size of your clock has to be large enough to accommodate the slowest instruction. That's something for computer engineers to discuss, not computer scientists for now. So single cycle, one instruction at a time, and you complete it before the next positive edge. We have been throwing this term data path quite a bit. Now let's formally define what the data path actually means. In data path, the elements that directly operate on the data, those constitute the data path. And they are actually controlled by a control unit, because you need a control unit to determine what kind of operation it is and which of the components, which of the Lego pieces in your data path should be active. Active elements constitute the data path. We are going to discuss control units at the end. And what we do is we usually design the data path first, because that's an easy thing to do. And then we determine the control unit, how to control the different Lego pieces. And here's the key to learning. The key to learning is construct hardware one step at a time. Take one simple instruction, make the hardware for it. Consider the next instruction, merge the hardware together. Then the next instruction, merge the hardware together. This is how computer engineers in Intel and NVIDIA, and even computer scientists in these companies, that's how they approach processor design. And we are going to keep adding to the hardware for the newer instructions. Okay, now, this is going to be the last item for discussion in today's class. In today's class, this is what we have done. We have determined what are the Lego pieces. We have determined how to bring those Lego pieces together to create your instruction fetching hardware. Then we brought some of the advanced Lego pieces to create our R-type hardware. These are the three takeaway things from this class: Lego pieces, instruction memory hardware, and R-type hardware. When you go home, please review these slides and be prepared for our next class. Before you go, here's what I would like for you to do. These are the different instructions: load word, add, and SW. Again, I would like for you to pair up again. And this time, partner to the right should explain the R-type instruction, and partner to the left explains the I-type instruction. And this is specifically what you're explaining. For each of these instructions, you have to identify what is RS, what is RT, what is RD, if any, and what is the immediate field, if any, and to which register bank ports should these go. That's what you're explaining to your peers. So partner to the right, take a look into the R-type instruction here. For that R-type instruction, identify what is RS, RT, RD, and tell your partner where it should go in the register file. And similarly, partner to the left, look into the I-type instructions there and identify the RS, RT, and RD field and determine where they should go in this register file. So please first work on your respective item first and then explain it to your peer.
I'm going to explain your item. S1 is the source, the input, we're going to store it. So you're going to take S1 and go to right register. Line 0 is immediate value. 0 is immediate field. S3 is read register. Read register 1. Read register 1.
Oh, and then we're going to do an art.
Yay.
And then roll it back.
So for I-type instructions, last one is SW. The four should be stored in different registers, right?
It's not actually a register. It's not a register. Your registers are only those with the dollar sign.
Yeah, I know, it's immediate value.
Yeah.
But the past immediate value here is the, yes, only register, right?
Actually, you know what? We don't need a new register. What you can do, see what's going to happen. In store instruction, the value which is in SP that is added with 4. Yeah, the value which is in dollar SP is added to 4, and your address classified.
Because the address.
So what you need to do is maybe send SP here, and out come the value of SP. Right? And then the immediate bits are last 15 to 0. So the value is going to be, so those 15 to 0 go into some sort of an adder or even ALU to produce the address, which then goes to a data memory.
Okay, can this thing be performed here before going there?
No, it cannot be performed there because you have to read it. It's happening here. See, when you do SP plus 4, it has to be read first. So it cannot be done here.
Here, I want to.
Yes.
Okay.
For example, if I were to say, hey, take a look on H.5. I have given you, I have put a value there. You have to add it to 4. Yeah, exactly. I tell you, now can you do that before opening the result? So you have to open it first and then.
And then in general, this is for your time. Are there several approaches, or is it only one correct answer?
No, there are several ways in which processors are designed. An Intel processor may be different than an processor. But their general structure, their most basic structure is kind of the same.
Okay.
So almost all processors have a similar blueprint.
So is it the same with the load word, the same operation, right? But it's just zero.
Yeah.
All right.
All right. Excellent. Okay, so before you all leave, I hope you were able to explain it to your peers. In the next class, I would like for you to create your load word hardware. So the group that creates the load word hardware successfully will get a sneakers from me. Okay. So what if you want 100 grand? The candy. Okay. So I'll check your work before the next class, before the start of the next class, and then if you're successful, you'll get a some sugar boost, right? In our next class, we are going to deal with the memory instruction hardware, and then we are going to look into the branching hardware.
Thank you.
Excellent.
All right. I think I should stop my
I don't know how you want it. You want it like this, with the text files already outputting.
Yeah, this has to be shoved into a
I'll
text file.
do that, bro.
Wait, what?
This has to be shoved in a text file.
Yeah, I made the text files, but
Oh, that.
do you want it like already the text file is showing, or
Your program can show, that's fine, but at the same time, the TA will be opening your text file. And it should be,
oh, so is he gonna like type in the text file himself, or
no, he's not. He is going to do nothing. This is what he's going to do. He's going to run your program.
yes?
And then he'll be like, okay, he'll type ls to see if out_code.txt is present there or not.
Okay.
If it is present, he'll open it and see what is there.
Yeah.
And then he'll check his own outcode.txt and see if they match together.
Okay.
That's how he's going to do it.
So I don't have to like open it, right? For the...
Well, you do have to,
Okay.
because your program should save these binary into outcode.txt.
Okay.
That's all he is going to do. So he's going to run your program. He will expect that your program would have written a file called outcode.txt with this binary. He'll open that file and see if the binary is correct or not.
All right.
Okay. Does that clear up?
Yeah.
Okay. Hey.
So, this one here,
Mhm.
instruction here, seems to be a trick question after some fashion, and I'm not really sure how. Could you tell me how?
No, this is not a trick question. why would you think that it's a trick question?
Because I'm getting the wrong answer despite getting everything. It's right. I feel like I have. The other ones are going okay, but this one's getting wrong. And it's the last question. But last question just. That seems like a place you would put it to a question.
Okay, so exactly where, can you tell me where it is going wrong? And how is it going wrong? Okay, you're getting this, is it? So,
And here it is broken down.
oh, okay. So here's what has happened. So you have encoded a binary 12. You literally took this and encoded it as 12. Now, for branching instruction, they're a little weird in the sense that whatever offset you provide, that has to be divided by 4.
Okay.
So in your functionality for branching, you did not divide this by 4.
Okay, branching is. Okay, which one's so that's anything that starts with a B, basically.
Yeah, B, well, in this case, just it's BEQ and BNE,
Okay, but that's the question. Is
Yeah.
that If it starts with a B, then we divide by 4.
and also jump, also the J instruction.
Okay.
For these 3, whatever offset you specify, you divide that by 4, and then you encode that. So 12 divided by 4 gives you a 3. You should have encoded 3 into binary. That was the only thing, and it's a simple fix. Hey, okay. So Corey, I want to talk to you. Okay. I want your success.
Yeah, exactly. B0, B1, B2, B3, right? Yeah. And I have to say, oh, that's equals to 1 and 2.
So you got it, Mo? Okay. Okay, but the idea is clear, right?